In the previous lecture, we finished discussing actor-only methods, and we discussed how we derive reinforce or policy gradients, right? And we went through the derivation. If you have any questions, please let us know in the comments below. In this lecture, we're going to continue on the course of reinforcement learning, and here we're going to discuss another method of how we are able to solve reinforcement learning, or MDPs, which are critic-only methods, before jumping into actor-critic methods. So in this lecture, we'll cover most parts of the critic-only methods, and then in the next lecture, we will go further. Okay, so in the actor-based methods that we took in the previous lecture, those were direct methods. In other words, those, you kind of search directly for the policy itself. So if you remember, we parameterized the policy by a deep network. And after we parameterized the policy by a deep network, what we did is we derived, this policy gradient update, right? And then we took gradient steps in the policy. Now, when it comes to critic-only methods, they are referred to as indirect methods. So those methods, they do not directly search for the policy. What they rather do is they build a notion of Q function, which dictates how would the policy would have performed. And then from that Q function, right, they try to deduce the policy. So we kind of deduce the policy from a Q function. So we call them indirect methods because we're not directly looking for the action selection rule. We rather build a Q function which reflects how well a policy would have acted, and then indirectly deduce a policy from that. So in other words, right, the pipeline of how critic-only methods operate, we will have a parameterized Q function, which I called here QWK. From that QWK, we deduce a policy, and we're going to talk how we deduce a policy from a Q function. But I think by now we should know how we do that from the previous lectures we've taken, because we could, for example, act greedily in the Q function, and that will give me the actions I could take, right? That's one way to do it. And then once I have this policy, I will play it in the environment. So I will play this policy, which I indirectly deduced from the Q. And then based on that, when I play that in the environment, I will get a performance measure of how good the policy is. And then based on that, I will try to use this performance measure, which I played in the environment, in order to update my estimate of the Q values. And that's why we call those critic-only methods, because what they are really doing is they are updating the critic, in this case, the Q values or the Q function, which is parameterized by WK. Indirectly, we deduce from that a policy which we play in the environment. And then based on that, we get the updates of the Q into QWK plus 1. So what's W here is just a parameterization of the critic or the Q function, which could be, for example, a deep neural network. And examples of those are widespread. I'm sure you've heard of them if you ever followed, the media about reinforcement learning. So, for example, fitted Q iteration is one of them, but maybe the most famous one that you've heard of is DQN, deep Q networks. And the idea here is what they are going to do is they're going to parameterize the Q function by a deep neural network, or double deep Q network, which was a follow-up work. But also things exist like Q learning and SARSA, and also LSTD. The drawback of this method is that if you have continuous action spaces, so if you cannot, list all your possible actions, then this could be expensive to figure out the policy from your Q function, because now you need to solve a maximization problem with respect to the actions in order, to find what action you should take at a state S, right? So in order, because let's be clear about this, right? So from the Q, we're going to deduce the policy. And the way we are going to deduce the policy is by, for example, being greedy in the Q. So meaning that we take argmax with respect to the action of the Q. Remember, the Q function is a function that maps from states cross actions to real numbers. So, we have a Q of S and A, Q of state and action. And then what we're going to do is now we're going to do, argmax in that queue with respect to the actions that belong to my action set, the allowable set of actions. Now, if these are discrete actions, then this is relatively easy to do. But if these are continuous actions, then this argmax is a bit harder to deal with. So it's kind of difficult to deal with. And that can be very expensive when we go into continuous action spaces. Okay, right. Now, the first algorithm, right, or the first update rule that we have for critic-based methods is what we call queue learning, right? And the update rule of the queue learning goes as follows, right? So here what we do is we update, so for a state action pair, so for some state ST and action AT, we update our estimate, right, of the queue. So we call that queue hat, right? So we update the estimate, right, of the queue at the next iteration k plus 1 as the old estimate we had at iteration k plus alpha times the reward you would get. So the reward you would get for the, this state and action AT, plus gamma times the max over the actions that you would get for the queue that you would get on A prime and ST plus 1, minus QK of ST AT. Now, we typically refer to this as the temporal difference error. And the idea here is that this rule, and I mean, there are proofs why this rule will recover Q star, of course, in discrete states, discrete actions. But the idea here is what I am doing, right, is I am updating my estimate of the Q value, okay, for that state, that action. So given that you have a state ST and you are, deciding, to understand what is the Q, of that state STAT at, some next iteration K plus 1, right? What we're going to do is we're going to use the old Q value. We're going to say, okay, that's the old Q value. Then we're going to multiply by some learning rate alpha. And then we're going to multiply that by a form of an error, which looks like this. So what's that error, right? So that's the error is going to be the reward, that we get, the immediate reward, plus, with a discount, because that's kind of looking into what would happen on the future state, ST plus 1. So we discount by 1 gamma. And we're going to see what's the max Q, right, that I would actually get, what's the max Q I would actually get on that state ST plus 1 if I select, so if I'm be greedy in it, if I select the max action. And then I'm going to subtract that from my current Q. So that's my TD error, right? So it's the error on which, how better off I would be if I select the max action, for the Q on the next state, added to that the reward and of course the discount of gamma, minus, right, the Q that, your current estimate Q. So that's how we would kind of do the Q learning update, right? So we kind of look one step into the future, right, with ST plus 1, be greedy in that, right, and then subtract that from QK of STAT. Now, notice that there are different variants of this Q learning algorithm, and we will go through them, but they will differ kind of by how much you're going to look into the future, and we're going to discuss that a little bit later. However, now we can look at the pseudocode, right, of the Q learning algorithm of policy TD control to estimate, your optimal policy. Now, this is coming from the Richard Sutton book, which is this book, right? So it's called, right, So it's called Reinforcement Learning, an Introduction. Right, so I think everybody should read this book. Sorry, it's not becoming clear on the picture, but the title is Reinforcement Learning, an Introduction, second edition by Richard Sutton and Andrew Bartu. I think this is now it appears. So this is a go-to book. If you're, trying to learn reinforcement learning, I would definitely recommend this book. Please go read it. It will have all the basics and everything we covered so far. And also it'll have some advanced stuff as well. So definitely a book to buy, a book to read. I have my copy. Please get yours. So the algorithm, the way this algorithm works is like this. So first of all, it has a set of hyperparameters. So The first hyperparameter is the learning rate alpha, which we're going to use, later on here in order to do an update for the Q estimate. And also we're going to have like an epsilon, which is going to be required for our exploitation trade-off. And if you remember from the previous lecture, we discussed the policy like epsilon greedy, right? With some probability you will take a random action, with 1 minus that probability you'll take a greedy action in the queue. And when I say greedy action, it means you do argmax, right, over the queue. Right. So now here what we have is we have a learning rate, and we have this epsilon, which we will use for exploration versus exploitation. The first thing we're going to do is we're going to initialize, right, all my states, we're going to initialize the Q value for every state and action. So for all the states and all the actions, right, we're going to initialize them arbitrary. So we're going to initialize them randomly, except for the terminal state. And the terminal state, we're going to give it a Q value of 0, right? So the terminal state, if you know your state is terminal, meaning you either stay there or you end or something, then this Q will be 0. Now, what do? Now you have 2 loops. So one loop is over episodes. So this is, how many big loops we're going to interact with the environment. The first thing we're going to do is we're going to start from some S, in my state space. So we initialize S. Then comes the second loop, right? So the second loop is for each step of the episode. So the first loop is loop over episodes, right? So episode meaning like trajectories, right? And then the second loop is looping over every step inside that episode. Now what we're going to do is we're going to pick an action, right? So we're going to pick an action from the state S using the policy from our Q estimate, right? So remember, we initialized our Q values here. So we initialized the Q for every state action pair. And now what we're going to do is, if we are at some state S, right, we initialize S here, right? So we start from this S. And if we are at that state S, what we are going to do is we are going to take an action A, which is according to my Q function so far. Example, by using epsilon greedy, meaning like you can take your action as random or, argmax in this Q for that state as, of course. So given that you are in that state, and then you've taken the action according to your Q value, current Q value estimate, then you actually take that action. And then once you take that action, you observe the reward, for that state action, and also you observe, the successor state where we go to, and then you will apply this rule right there in order to update the estimate for your Q, S, and A, and then you repeat this until the S is a terminal state. So you'll keep doing that until the S is the terminal state where the Q value for that will be 0. So essentially, right, what is happening is we are starting, from like here, we are saying, okay, let's take some state, right? And now when we are in that state, right, what we're going to do is we're going to choose an action, from that state. And the way we choose that action is according to our Q estimate, which is SA, right? Q of SA. That's a Q of SA. And then based on that, I will go to some new state S prime, and then I will get a reward, right? So that's the reward, and that's the S prime. And now, given that I have those, right, then I'm going to follow this rule which we described here, in order to update my estimate for Q, S, and A. So what I do is I say my new Q, S, and A, so my new Q value for that state action pair, is my old Q value. So in the first iteration, it's whatever I initialized, right? Plus this learning rate, the hyperparameter alpha, and multiply that by the reward we got for this transition, right? That's the reward, plus gamma max over Q of S prime and A. So when we are here at S prime, right, we can compute this max over A of Q of S prime and A, right? So here, for example, you can try all the possible actions, and then based on that, you will take the action that corresponds to the max Q, right, at S prime, You might ask, where does this Q of S prime come from? Well, we initialized the Q for all states and actions at the beginning, right? And then later on, we're going to observe it, and then we're going to do the update, right? And then you subtract that from Q, S, and A, and then that's how you'll get your update for the Q value for that state action pair. And then you repeat this until, the thing is, until you get the terminal state, okay? So to recap, what is really happening, right, is, as we said, we start at the state, right? And then we're going to pick an action. Notice how we pick the action. So the way we pick the action is by, for example, an epsilon greedy strategy from the current to Q estimate. So we can say this action is either argmax, right, of Q, S, and A, or with the sum probability 1 minus epsilon, or with probability epsilon is a random action, allowed from the actions allowed in this state. That's going to take me, right, to S prime and will give me a reward R. Notice that for S prime, I can also now compute the Q value, right, for S prime A, right, because I initialized it at the beginning, right, and if I've seen it before, then I would have updated its estimate. And then what I do is I take the argmax of that, multiply by gamma, which is the discount factor, typically 0.9. And then you add R plus gamma max minus Q, S, and A, right? And then that's the update, for this Q value of S and A. And then you repeat, and that's it. So this is all Q learning, or Q of 0, right? That's what we call it. Okay. So hopefully that's clear, right? So what we do is we update the Q estimate as the old Q estimate plus alpha times this term. This monstrous term is what we call the TD error. And it is simply the reward plus gamma max Q over the successor state minus Q state action at ST AT. Okay, good. Now, for example, there are other forms, right, of this update. And those other forms of this update, for example, one of them is called SARSA of 0. So SARSA of 0 is very similar to Q learning, but it tries to be a bit less greedy in the successor state, right? So instead of it saying, I'm going to take the new Q to be the old Q plus alpha times the TD error, which we had before, now what it's going to do is not going to take anymore the max, right, that you've seen here over the TD error, right? So it's not going to take the max as we've done before. So where we've taken the max over all the possible actions. Here, this is going to be just computing the Q over ST plus 1, AT plus 1. So let's go slowly through that. So again, from the book, right, that I showed you, what we're going to do again is the same thing. We're going to initialize the Q for all state action pairs, for all state and actions, except the terminal, we're going to give it a Q of 0. Then we're going to start from some S, right? So we're going to start from some S, right? So that's S. Then we are going to take an action A according to an epsilon greedy strategy in the Q, right? So, as we said, A is going to be argmax over Q or just some random action. And that takes me to S prime, okay? That takes me to S prime, and I observe a reward R, right? So take the action, you observe a reward R, and you observe the new state S prime, okay? Now, from S prime, before, right, we were taking the max, right? So we were just saying, okay, we're going to take the max over A of Q of S prime A. Now, instead of doing that, what we're going to do is that we're going to choose an action, so we're going to be not greedy, right? Necessarily greedy in all the possible actions that I can take, but actually what I'm going to try to do is I'm going to choose an action A prime in this state S prime. So remember, I'm in this state S prime now because I was at S. I applied an action A according to epsilon greedy in the current Q estimate. That took me to S prime, and I observed a reward R. Now what I'm going to do, right, is given that I am at S prime, what I'm going to do now is I'm going to take another action. So I'm going to take another action A prime, right? And the way I'm going to take this action A prime is again by being, right, greedy in the current Q value, right? So in the current Q estimate, I'm going to be greedy. So as I've taken an action here, right, I've taken action again here, okay? And now instead of doing the max as I used to do in Q Learning Zero, now what I'm going to do is I'm going to just have the Q, right, which is the same as we had before. Then I'm going to have the learning rate, right, which is the same as I had before. Then I'm going to have the reward that I got for my transition, right? But now, instead of doing gamma max of Q over A, max over A of Q of S prime A, I'm going to take the Q of S prime A prime, right? So I'm going to take the Q value corresponding to, S prime A prime, okay? And subtract that from Q, S, and A, okay? And I'm going to repeat that until the state is terminal. So essentially, if you compare those two together, you would notice that in the Q Learning Zero, right, we had a max over the actions, right? But here we're not having the max over the action. But what we're going to do is we're going to choose an action A prime there, and then take the Q value corresponding to S prime A prime, and then do the same TD error update rule. So I'm going to take the old Q, multiply by a learning rate, and then here have the TD error. But now the TD error does not have the max anymore. It's just now Q of ST plus 1, AT plus 1. Okay. Again, this algorithm is from the Sutton book. Okay. So this algorithm, we call it SARSA 0. And the previous algorithm, we called it Q Learning 0. Now, in general, right, we can ask the question, is that how can we estimate the value, right, of a in kind of model-free algorithms, right? Because if you really notice what we are doing right in here is that these parts, these components, right, they are kind of corresponding, to actually a value estimate, right? So now we can ask the question, right? So how can we estimate the value? How can we estimate the value function, right, in model-free algorithms? Okay. So there are multiple ways to do this, right? So there's a one-step methods, there are two-step methods, there are n-step methods, and there are infinite step methods. Okay. So when it comes to one-step methods, what we do, right, we estimate the value function is just based on the instantaneous reward, right? Plus gamma times the estimate of the V or the estimate of the Q only on the successor state, right? So if we are, at ST, right, and then we went to ST plus 1, right? Now what we're going to do is we are going to estimate the value simply by RT plus gamma of ST plus 1 and AT plus 1, as we were doing here, for example, right? So here we only cared, right, for the ST plus 1, AT plus 1, okay? And here I just write V hat or Q hat just to say that this could work if you're doing a value-based iteration, like a value-based critic, or if you are doing a Q function, right? And as we took before, there's a relationship between those two. Okay, now that's one step. However, you can do also two steps, right? Not only one step. So what you could do is you can consider your instantaneous reward. You can consider your next step reward that you would get. So we would do two steps, you would get two rewards, RT plus 1. And then you can consider, the Q or the value you would get thereof, you get from T plus 2 forward. So what you could do, right, is you can say, okay, it's going to be RT, right, plus RT plus 1, but notice that we have the discount factor, right? So the next step reward is discounted by gamma, and the next step value will be discounted by gamma times gamma, it's gamma squared, right? Because remember our equation, it was summation of gamma to the power T. So when T is, it's the first time step, it'll be gamma. So that's why you see here gamma. And then if it's the second time step, then that would be gamma squared. Okay. And then here you can do the same, but with the Q estimate. So here you can say it's RT plus gamma RT plus 1. So two steps, first step, second step, and so on. And the Q thereof from ST plus 2 forward, ST plus 2, AT plus 2, from the T plus 2 onward. And please notice, right, that this is the Q hat estimate, and that should be multiplied by gamma squared. Right. So just to be clear on this, right? Like if things are confusing at this stage, right? So at if you remember our equation for the reward, right? For the sum of reward, we had you would have RT, plus gamma, RT plus 1, right? Plus gamma squared, right? RT plus 2, right? Plus, whatever, T plus, sorry, plus 2, plus gamma cubed, RT plus whatever 4, and so on, right? So forth, right? This was like the summation of gamma T RT, right? Now, all we are doing really is that we are saying, okay, if I'm working with one step, then I'm just gonna be interested in observing this reward, right? And then I'm gonna try to have an estimate of these things to go, right? And that's what we're calling, like, for example, Q hat ST plus 1, AT plus 1, right? Or if you're working with value, it's V, V hat ST plus 1. Now, if you're working with two steps, right, we are saying, okay, you're going to observe this guy, and from here onward, right, we're going to try to do this estimate, right? And then now, if you actually look into this, you can rewrite it in this form, and so on, right? So this is just a way, right, where we estimate the value, of the policy in the model-free methods. So we've taken the one-step estimate, we've taken the two-step estimate, but can also do infinite step estimates, right? So we can do like as much as we want. We can kind of try to run as much as we want. And in this case, you would actually have the whole sum, right? So you will be talking about RT. We will be talking about gamma RT plus 1, so first step, second step, plus gamma squared RT plus 2, plus gamma cubed RT plus 3, and so on. And now you'll end up with the summation from T equals 1 to L of gamma T minus 1 RT. Now, what we typically use, right, is we use n-step returns in the implementation of these RL algorithms. And the idea there is that when we talk about n-step returns, is that what we're going to do is we're going to observe the reward for, n transitions, right? And then we're going to have the estimation of t plus n, like the value from t plus n forward. So, for example, these look like a messy equation, but it's okay. We're gonna look at that. And this is actually a very important trick in Critic algorithms. It works really well. Now, the idea here is that, the return, right, for the state ST, the n-step return, right, the n-step return. So we're going to observe n transitions, right? We're going to look at these n transitions. So let's look into this equation. So we have the summation from I equals T to T plus n minus 1 of gamma I minus T Ri plus 1. Okay, and now let's for a second forget about this term. Just let's understand what this term looks like. Okay, well, let's loop this forward, right? So it will start from I equals T, right? So when I equals T, it will be gamma of T minus T, which is gamma to the power 0. And then I is T, so you'll get here RT plus 1. Okay, plus, now when T is equal to T plus 1, so you will have gamma of T, is equal to T plus 1. You will have T plus 1, minus T, so you will get a 1 gamma, and then you get RT plus 2, right? And then let's go on, right? And then dot, 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 dot. And now let's look at the last term. So when I is equal to T plus N minus 1. So when I is equal to T plus N minus 1, what do you get? You get gamma. And instead of I, we're going to put T plus N minus 1 minus T, right? And T blah, blah, blah goes away. So you get gamma N minus 1. And then here you will have R. Instead of I, you will put T N minus 1 plus 1, right? Then you will get T plus, right? So as you see here, these are the return, for the first, second, up to the nth step, right? Oh, sorry, the reward, not the return, sorry. These are the rewards for the first, second, up to the nth step, and they are discounted, by, their corresponding gamma, right? So it's like similar to, what we've done here, right? Well, we kind of roll that up to n steps, right? Okay. And then, right, and then once we've run that up to n steps, right, So if we go back here into this equation, right? So we said it's going to be RT gamma RT plus 1 gamma squared V blah blah blah, right? However, if we are doing n steps, right? So you should have the summation of the rewards up to that n step plus some gamma to the power, it's 2 steps gamma squared, it's n steps going to be gamma n, and the value of the state, the estimate of the value of the state t plus n. Okay, so you observe the n steps and then you estimate the value from that moment thereof. Okay, is this clear? I hope. If not, please write me in the comments. I can try to explain it again. But this is going to compute for us, the n step returns, which includes, the rewards corresponding to n transitions, and then, the estimation of the future thereof. Okay. Now, if we were doing like Q-learning, right? If we were doing Q-learning, the way we could compute the return, well, if you remember, let's go back to remember our equation, right, of Q-learning. So Q-learning would have said RT plus gamma max, right? And this is, just Q-learning of 0. Now, Q-learning of n steps into the future, right? What we would have needed is we would need to observe n transitions. So that's this term and this term are the same, and this will be just the sum of the rewards. And now here we're going to take gamma n, and then we're going to take the max of the estimate from t plus n forward, right? So from t plus for the q hat of st plus n a prime. So in other words, it's the same thing as this equation, but instead of t plus 1, we're going to have t plus n, and instead of 1 RT, right, we're going to have n of those. And instead of gamma, we're going to have gamma raised to the power n because we have made n transitions. All right, that's that. And now if we were doing SARSA and not Q-learning, right, and we want to do we want to use n step return, then what will happen is that the equation will stay the same as before, right? So this is the same equation we had for SARSA. However, now instead of observing 1R and 1Q, now we need to make sure that we have observed n of them, right? So that's why the equation will become something like this, where now you take the n transitions, which you observe the rewards, and then you estimate the future, right? So you estimate the future from that moment onwards, right? And then that's st plus n at plus n. Okay. Right. So what we've done in this slide, right, is that we talked about, how we're going to estimate the Q, right, of the future, right, or the Q function or the value function in model 3 algorithms. We said we could do it using one step, where we actually just take one step, observe the reward, and have the estimate of the discounted rewards to go in the future. We said we can do it in 2 steps, right? We take the first step, the second step, right? And then we just have the discounted prediction or discounted estimation from that moment on. Or we can do it via n step, right? Where n step, what we actually do is we just take, n steps, observe the rewards, and then from the t plus n, so after, we've taken n steps, we try to estimate from that moment onward what the Q value would have looked like. And this is kind of depicted pictorially, here where, this is one step after ST plus 1, you do an estimation, or after 2 steps, you decide to do an estimation, or after n steps, or you just don't, and then you do a Monte Carlo estimate. Okay, so far, right, we have discussed, Q-learning of 0. Oops, let's go back. So we discussed Q-learning. Okay, so first of all, we talked about critic-based methods, which are indirect methods. You kind of estimate the Q, and then you play the policy, and then based on the return, you try to update the Q. We talked about Q-learning algorithm. The Q-learning algorithm, you just take one step from your state action according to your Q function, greedily maybe, or epsilon greedy in your Q, in your current Q estimate, and then you will take the max, and then you would add to that a learning rate, multiplied by the reward you would get for that transition, and then you would multiply by gamma, you would add to that gamma, and then you take the max over the Q from ST plus 1 onward, and you subtract that from the Q hat, which is your current estimate. Then we talked about SARSA, where we said SARSA of 0, it is actually, this rule here, where instead of going the max, we're just going to take, Q of ST plus 1, AT plus 1. But then also we talked about different forms. So for example, we talked about n-step return SARSA or n-step, Q-learning, n-step return Q-learning. And then we said here that for the n-step SARSA, what we're going to do is we're going to, kind of observe, n transitions and then estimate from that forward. The way we estimate is using the Q hat equation of SARSA, which was just saying we're going to take Q, of ST plus 1 AT plus 1. And then here what we're going to do is the same, Q hat ST plus N AT plus N. And then in case of we're doing Q learning, we would have taken the max. Okay, so what's the difference here? The difference is what we observe and what we kind of predict, right? So what we're observing and what we're kind of predicting. So if we go back to like this Q learning, right, we actually, we were taking the action, observing the reward and only the successor state. Similarly in SARSA, right, we were taking the action and observing the successor state, but then we were taking another action in the successor state. Now, if you're doing n-step return, you take n actions. So you start from state, you take the first, second, third, etc., and then you would observe those returns, and then the things that you don't observe and then you want to estimate from that moment on, that's where you replace your Q hat in, and then there's a gamma to the corresponding power, that you would need to multiply. Okay. All right. Yeah, so that's what we've taken, right? So that's what we've talked about. These are the n-step returns. And now let's just talk about one more thing, which is the lambda returns. So these lambda returns, right, what happens is as follows. So you would start from S0 and you would take an action A0 that will get you, to S1, A1. From that, you will take another action A1 that will get you to S2, A2, right? And then from that, you would also go to A2 and then you would apply A2 and then you would get to S3 and then reward R3. And then, you kind of continue, right, this forward, okay? But now here we introduce, this parameter lambda, and this parameter lambda kind of is going to trade off two things, right? So it's going to trade off a Monte Carlo return, which is just the sum of the returns you would have gotten, and kind of the estimate, right, that we have here. That's kind of the estimate, that we are estimating. It's just kind of doing this linear combination or trade-off, between these two components, and then we call that TD lambda, or temporal difference learning of lambda. And now, if we are talking about Q learning lambda or SARSA lambda, the main difference that you will have, compared to the previous algorithms is that you would actually use, this estimate of the reward or of the return, instead of the, previous estimates that we discussed before. So here you would see that now the update rule, right, will be looking the same as before. So you'll have, your new Q is your old Q plus learning rate. But now instead of this odd intermediate reward plus gamma, etc., now what you actually do is you use this equation which trades off these two components together, right? And then you subtract that from the current estimate you had of ST and AT. And now that way, right, we are able to kind of do the estimation when we are talking about Q learning lambda or SARSA lambda. Okay. Now, so all those, all those are interesting, but they motivated maybe the main development of the critic-based algorithms, which is really DQN or deep Q networks. So deep Q networks is one of the most important algorithms, right, that has been devised in the recent history of reinforcement learning. It was a algorithm from DeepMind, and that algorithm I think was published in Nature, and it was for the first time the first algorithm that was capable of solving a lot of Atari games. Now, what this algorithm is really doing, it's simply executing Q learning of 0 with a neural network. So remember Q learning of 0, which is kind of this algorithm here. But now what they're going to do is they're going to parameterize, this neural network, this Q function by neural network, and then they're gonna kind of update the weights of that neural network based on transitions. So it had three main components, Q-learning, right? So first of all, it was the application of Q-learning 0, but it used the neural network estimation, to represent the Q function. It had a replay buffer, and that replay buffer was actually storing, state, action, successor states, and rewards. And then they had a target network to stabilize a bit the training. And that target network, kind of was the same Q network, but frozen for some time before it gets updated. And in fact, there's a recent paper that actually argues we don't need the target network. I think the authors have given a talk in METI with a fantastic researcher. And I think this was the talk about batch normalization, right? If I'm not mistaken, batch normalization in RL, where they actually said we don't need the target network anymore, if I'm not mistaken. But let's talk a bit about deep Q learning. So the idea of deep Q learning is that you are going to parameterize your Q function, right? You're going to parameterize your Q function, okay, by a neural network, by a deep network, and that deep network, right, is going to act in the following way. So we're going to work in a discrete action space. So we have, an action, 1 to up to an action. And then the network will take as an input a state. And then on the output of the network, it will give you a Q value for every action. So it has like n heads or n outputs depending on how many actions you have. And then what this network will do is that this network will actually map from the state into a set of Q values. So Q, the first here will be Q. It will be predicting the Q for the state and action A1, right? The second output here will be Q for that state and action A2, right? And up to, Q of that state and action AN, all right? And now that state here, right, is mapped to this Q over, these actions, SA, via a deep neural network. Okay, now that neural network, right, is dependent on the task that you are solving, but the authors, I believe, originally considered Atari games, and the state in an Atari game was the image, of the environment of the game. So that neural network was a convolution network, where, a convolution neural network, where the input S will be an image, and then, for every action, it was predicting a Q value. So the first thing they do is they represent the Q, by neural network. They have a replay buffer, right? So this is like a memory of state, action, successor states, and rewards, that like these four things that we have been seeing, and a target network. The way the algorithm works is as follows, right? So first of all, we initialize, the replay memory to, some capacity n, okay? Then we initialize the action value function Q with random weights. So essentially all it's saying, this is a neural network, and the first thing we're going to do is we're going to set, we're going to start with theta, which are the weights of this neural network, to be random, right? So like we do in any standard neural network, right? When we start, we just say, okay, we're going to kind of start with random weights of my neural network, okay? Then we're going to run over episodes, right? So episode 1 up to episode n. Okay, and then inside this episode, right, where each episode has a length t, so we have two loops, one over episodes and one over the length t. The first thing we're going to do is we are going to with a probability epsilon select an action AT, right? So we're going to select an action AT randomly with a probability epsilon. Otherwise, select an action AT with the max over the Q. Okay. Now, what is this really, if you think about it? This is kind of an epsilon greedy strategy, right? Where it's saying with some probability epsilon select a random action, otherwise be greedy in your Q value. And now just notice here, right, that we have something called phi, right, which is kind of a pre-processing of a sequence, and that is needed, in case like because if you're trying to solve maybe some Atari games, then you might have a couple of frames that you want to connect together, or so on. And this is just a pre-processing step that you would actually do. Now, what you do is after you select the action, then you execute your action AT in the emulator of the game. And then you would observe, the reward and the image xt plus one, right? So you would observe the from the emulator, right? You would observe the reward and the, image xt plus one. Now the next state st plus one is the old state and the action, and also, this xt plus one, which is, the image we got from the emulator. And then we're going to also pre-process, according to whatever pre-processing function we have, this state st plus one. And then we're going to store, the phi t, which is the representation, of the previous state, the action we chose and the reward we got, and phi t plus one inside my replay buffer. Okay. And now what I'm going to do next, right, is I'm going to sample a mini batch from my replay buffer. So I'm going to sample phi j, aj, rj, phi j plus one. And then for that, I'm going to have a kind of a set of targets, that I would like my network to try to follow. And this is kind of the estimate, the improved estimate of my Q. So it's going to be either the reward if I'm at the terminal state. Because remember, we said that if we are at terminal state, we set the Q to 0, right? Like if you remember from our previous slide. And then what we're going to do, if it's not terminal, we're just going to do this TD error, where we're going to take the reward plus gamma, and then we're going to be greedy, in phi j plus 1 or sj plus 1, really, which is kind of the pre-processing of where phi j plus 1 is pre-processing of sj plus 1. And now once I have those, yj's, now I'm going to try to update the weights of my neural network in order, right, to be able to kind of estimate or be close to the estimates of my y's that I have gotten yj here. And that would be either, that would be simply performing an MSE loss between the yj and the q, which is just the yj that you got here, minus the Q for that phi j and that action aj that are available in your replay buffer. And then you square that, and then you take a gradient step in this. And then you repeat. That's all this is. So what we do is we first initialize it, right, with a, we first represent the Q by neural network, and then we just initialize the weights randomly. And then after we initialize the weights randomly, we then take an action with an epsilon greedy procedure. After taking an action, we execute it and we observe the image, which we then pre-process. We store the phi t, which is the pre-processed of the st, and the action at, the rt phi t plus 1 in my replay buffer. Using those, then I will just compute a set of targets that I want my network to follow. And those targets are just, simply the reward if I'm at a terminal state, or the TD error. I mean, as you remember from here, right? Because we said if it's terminal, we're going to set the Q to 0. Otherwise, we're going to, consider this is my TD error, right? R plus gamma Q. So all I'm doing here is the same thing. I'm either saying it's the reward if it's the terminal state, or it's the TD error, and then I'm going to regress that. And that's all this DQN going to do. Okay, so before continuing, right, I think next time we can dig a bit deeper and review, right, Q learning and also lambda returns. I think these are two important concepts we should not forget about. And what I would like you to do is to try to understand in details those algorithms. And if you have any question whatsoever, please write us in the comments below, and then I will be very happy to answer. So next time I'll go again through, DQN if this was not clear enough. And then we're gonna kind of continue, in our derivations and maybe talk about actor critic methods. But so far, we have covered reinforce in the previous lecture, and today at least we understand what Q-learning is, SARSA is, and we touched a bit upon DQNs. And with that, I would like to end this lecture. I would like to thank you. I would like to urge you to subscribe, like, and share if you found those are useful. And I will see you next time where we repeat the QN maybe a bit and then discuss things related to actor critic methods. So thanks a lot, and I will see you next time.